Hi, this is Vishal. This is my quick summary of the videos that I've been watching for the analysis of algorithms. Since I know usually most of this stuff, it's helpful for me to first look at the lectures and then just make a brief video which summarizes what I learned from these lectures so that I can quickly come back to it and have a quick revision, so as to speak. So that's where I am coming from. Okay, so let's start. I'm going to do this for a set of videos. I'm going to make one of my own video, and hopefully I can get like an hour's worth of videos into 10 minutes or less. That's kind of the idea here. Okay, so the first set of lectures starts about algorithms. Why study algorithms? So the algorithm, you basically, there are two things. Programming is algorithms plus data structures. That's kind of the idea here. And you want to understand the data structure, and you also want to the data structure is things that where does your data go, and algorithms is what you eventually do with it, the workflow, so as to speak. So that's that's what it is. So this is the part one of algorithms course, which is going to cover these things: data types, sorting, searching, and part two is going to cover graphs, strings, and more advanced algorithms. So why it's I don't know too about it. It's being used everywhere. You need to know this stuff, and yeah, it's been around for a while, and I think this is kind of this evergreen field. This is the basis of everything. Okay, so now the idea is, why do you need to study something like that? A professor starts with an example of union find. Let's say there are all these various connections, so two dots, and there is a line between this dot represents of connection between those two, and you want to find out, is there a connection that exists from point A to point B? What it means is, is there a path from point A to point B? How do you find it out, right? So these kind of things, you can figure that out, and it's basically yeah, it's kind of smart. It makes it's neat, it's smart, and it helps solve a lot of problems. And this is the idea, algorithms is equal, algorithms plus data structures is programming. So that's kind of it. And what does Linus Torvalds say is that the difference between a bad programmer and a good one is whether he considers his code or his data structure is more important. Bad programmers worry about code, good programmers worry about data structures and their relationships. So that what it means is, you need to figure out at a high level how you need to do things before eventually worrying about code. That's the idea. You need to think about what your program is going to do, how is it going to do it, before you actually get into the nitty-gritties of the actual implementation. And why study algorithm? I'm going to skip that. Yeah, if you want to get a job into any of these large companies, you need to know algorithms. That's true for the company I work right now. And yeah, it's a lot of fun, and it makes us smarter. So go for it. Anything else? Yeah, I think we require programming. I'm actually going to do C++, C++. Professor takes up Java. I know C#. Hence I think I know Java as well. It's been a while. I've been rusty in C++ for a while, so I'm just going to do that to kind of brush up my C++ programming skills. Okay, so now so this is the first lecture. Now let's talk about analysis algorithms. Or should we know? We should do union find first. So union find, what is the problem? And this is the kind of problem that professor uses. Let me get the professor's correct name. That Professor Robert uses to motivate and build all these constructs. Okay, model the problem fast enough. So this is kind of an example problem which bootstraps our way of thinking about the code and about algorithms. Okay, so what is the problem? It's about union find. What is union find? So it is similar to what the example that we just looked at. So let's say there are a bunch of nodes, 0, 1, 2, etc., and there are connections between these nodes. A connection between 0 and 1 is a union 0, 1. Okay, so union 4, 3 means 3 and 4 are connected, etc. And now given this, given a set of objects, nodes, and a set of unions, you want to find out whether any two nodes are connected. For example, are 0 and 7 connected? Well, not right now with these things. This graph represents the final picture. Sorry, this graph represents the final picture. But what? So with just 4, 3, 3, 8, 6, 5, 9, 4, and 1, 2, it's not connected. But when you add some more unions, then 0 and 7 become connected. That's kind of the idea here. And then how do you find out complex problems? As you can imagine, this is if you can solve that, then you can also solve this. And there are various other applications of the union find problem. Now, how do you model this? So first we assume that it is equivalence relation. What that means is there is no directionality. P is connected to P, P is connected to Q, then Q is connected to P, and it is transitive, A to B, B to C, then A to C, something like that. So that's what it means. It's an equivalence relation. And we define another concept, that is connected components. It means it's the maximal set of objects that are mutually connected. What that means is you cannot say 2 and 3 is a connected component. You have to include this entire set. That's the idea here. It's a maximal set. So what that means is nothing more can be added to it. So we find query, we understand that, and union is to just join two things. Okay, so we understand both these two. So goal, we want to find out this efficiently. So as you can imagine, the number of objects n can be huge. So you want to figure out in a very quick way. You want to be both efficient in terms of memory and also time, because n is number of objects and number of operations. Union operations can be huge, and then queries and operations will be intermixed. What it means is, think of Facebook, right? Your graph will always continue to grow, and people will always try to find out, who are your friends, something like that. So so that's the idea here. And professor talks about that you should always have a test code to test your algorithm before you actually write code for the algorithm. It's kind of the test driven methodology. I think that's always a good thing to do. So now let's look at the real problem. So quick find. So this is the first approach. Okay, so union find is the problem. This is the first algorithm, is quick find. So what the quick find does is that here's the basic idea, that all the connected nodes or the connected set have the same ID or the integer. What that means is, see, 0, 5 and 6 are connected, so all of them have the same identifier, which is 0. So if you want to find out whether any two nodes are connected, they should have the same identifier. That's the basic idea, correct? Okay, so what that means is, okay, so let's see how this is in action. Okay, so if you want to merge, if you want to union any two, you want to merge two nodes P and Q, what do you want to do? You want to change all entries whose ID is equal to IP to IQ. What that means is, if after union of 6 and 1, you want to look at 1's ID, correct? That is 1, and then change all of 6 ID. So 6, 5, 0. So 6 had the ID 0, and these are the other elements had the ID 0. So you change all of them to 1. So that's the idea. You can do it in either ways. You could have also changed all of 1's to 2. Really doesn't matter. So you can do it either ways. Yeah, really. And here's the demo. Obviously, I don't think I can show you the demo, but you get the idea. Okay, so when you do this demo, this is what happens at the end. The implementation, let's not worry about it, but let's talk about the cost, right? So initialization is n, and every union operation may take up to an order of n. What that means is you will have to update, you will have to touch order of n nodes to update their IDs, correct? So let's say if there are, what it means is, here if you come here, in this kind of a thing, you have touching, when you union 6 and 1, you touch order of n. It's an order of n. In this case, the explicit number is 3, but you can imagine you may at most touch all of them. You're almost touching all of them every time. That's possible. So that's the idea. It's an order of n. and we talk about order later. So in this case, the total, if there are n union operations and each union operation takes n accesses, then the total is order n square. So it's quadratic. So the growth rate is quadratic. This is kind of very expensive. And typically what will happen is the brute force method is usually the most expensive one. So then he talks about how quadratic algorithms do not scale. This is kind of the growth of quadratic algorithms. There is another nice thing which the table that we can look at later. So what is quick union? So we looked at the first one, we look at quick find. Now let's look at a variant of it, quick union. And in this case what we are doing is, instead of the union operation is expensive right now, so we'll make that cheap in the way that we will not have to update all these IDs. That's the idea. And what do? You just, when you want to union 9 and 2, you just connect, you have a pointer of 9 of 2 to 9. That's what you do. You point 2 to 9. Now, so what it means is you start with the initial, well, this is kind of the final set of pointers. So that's the idea. So that means is 5 is pointing to 6. Now if you want to union something to 5, let's say there's a number 10 that you want to union to 5, you'll add 10 and you make the ID of 10 as 5. Right? So you're not changing this entire chain, you'll just change the ID of 10. And if you want to see whether 5 and 10 or any such things are connected, or 2 and 3, you will see that whether all of them have the same root. Okay, so they all can trace back to the same root. In this case, what you can see is, okay, so that's the idea. Okay, so that's the union to merge and when you merge your P and Q, set the ID of P's root to the IDs of Q's root. So we spoke about that, correct? If you want to merge 3 and Q, then you point the root of this, which is 9, to the root of 5, which is 6. So that's how you will merge both of them. So once again, only one value changes. We initially explained the simple case where there's only one element, 8, and that needs to be pointed to, let's say, 5. Then 8 will I'm sorry, I said something wrong. 8 will not point to 5. 8 will point to the root of 5, which is 6. So it will just directly point to 6 in this case. Okay. When you're trying to union 5 and 8, so that's the idea. So root of 3 is 9 and root of 5 is 6. Okay, so 3 and 5 are not connected to this. This is just giving an example here. Okay, so once again a demo. We cannot show the demo right now, but that's what do you want to imagine how this will come to be? So let's take a look at it. So what probably happened is you connected. Okay, so let's see. So this is a flat tree. Now how do you go from a flat tree to something branched like this, right? So as you can imagine here, 6 and 5 are connected. Now if you wanted to connect 3 and 5, you will connect 6 to 9. So that's how you get the branching, so as to speak, right? So it will not always be flat. You will kind of grow like that, and you will get all these weird structures at the end. Okay, so that's the idea. Some implementation, but at a very high level, you can now immediately see that the union operation is very cheap. It's no longer order n. You're no longer updating all of them. You are traversing the tree though. What it means is you are going to go up the tree to find out what the root is. In this case, so you'll have to touch some things. You'll have to make some pauses, but that's the idea. Okay, so here's the implementation. So quick union. This is the worst case scenario. You'll have these are very flat, very tall trees. So these are worst case scenarios. Okay, these can get very tall. That's kind of the problem. Okay, fine to expensive. Again, you have to go to the root and figure things out. So both union, so that's the idea here. Fine can be too expensive. Instead of order 1, it was just the idea you have to climb this entire tree, find out this root, climb this entire tree, find out this root, and you can imagine, this is very expensive. Okay. Now the quick way to improve the union find is, okay, it's a very simple idea, is the weighted approach. So instead of the smaller to larger tree, you always make sure that the smaller tree is connected to the larger tree. That's the idea. So this is quick. What it means is you're trying to make sure you don't have very tall trees. That's the defect you're trying to solve. And then this is the idea here. it's more flattened. This is another example with quick union and weighted. As you can see, this is much more flattened, and the idea here is, the depth of at most any low node is log n, and you can imagine that, when you divide it by 2, if it is if this one is already taller than this one, then you will not add it. You will kind of, sorry, let me state that well. If you already have, for you to become taller, you will have a complete set of nodes that are less than your height. So what it means is you're kind of halving that. So that's the idea. And why it can be at most log n is, log, and 2 to the power of log n is n. So that's the idea. And there are n nodes. Yeah, so some more things. So that's the idea. Union takes log n, and find takes at most log n. So that's the main thing, right? And as you can see, now suddenly you've gone from a n squared to n log n solution. And can we improve further? So yes, you can do something called as path compression. Just after computing the root, if you already know once you have kind of found the root of P, let's say there is a find operation and you have found the root of P, for every node that touched, that you encountered when you found the route, just make all of them pointing to the root directly. So you're flattening the tree more. That's the idea. So it's called as path compression. And then this becomes much better, and in terms of analysis, this is log star n. And there is something which is called log star. I actually forgot, but the idea is log star n is grows really, really, really slow. Okay, so it's as good as a constant function. So that's the main idea here. So yeah, so in terms of analysis, the quick find worst case is mn. This is mn, so it's still order n squared. That's how I think about it. This is n plus m log n, and this is once again m log n. So again, you have gone from n squared to n log n, and now you have gone to m log star n, which is almost m. So what it means is it is actually just a constant, much better than that. Okay. Applications. So there are lots of applications. One interesting one is that you can do a Monte Carlo simulation and figure out, given a set of, when you're trying to find out connected, whether this is connected, what it means, whether water will flow from top to bottom, etc. What is the probability P that you need for something to be turned or to have a connection or not, and find out what is the threshold. And turns out, the P has a threshold like that, and it's called a site percolation probability. So we spoke about Monte Carlo, and the union find and quick union find enables you to do this. What that means is you can have a virtual root and a virtual bottom, virtual top and a virtual bottom, and then figure out whether the virtual top and bottom connect to each other. So in that case, you know whether this whole grid water can flow from the top to the bottom. In this case, it can't. So that's the idea here. Okay, we spoke about this, applications, and that's it. So we'll now talk about the next set of. We covered lectures 1 and 2, and now we'll talk about lecture 3 in the next one. Okay, thanks, bye.